SwayamPrabha. Digital India. Educated India.
Hello all. In this video we will be looking at the advantages and various applications where composites can be used. First we will start with the most commonly cited advantage of these composites, which is the high specific strength and specific stiffness. And because of these specific strength and stiffness, it improves the performance. So most likely this performance is where we need it in aerospace industry, automotive industry, or even like the sports industry, where we want to improve the performance of these structures or where they are used. And because of these specific strength and stiffness, which means we can get high strength and stiffness at less weight, it indeed saves the fuel. So for example, in the aerospace industry and automotive industry, saving the fuel is very important just because of the economics. In addition to these, there are several other advantages such as the tailored design. So here we will go into the greater details, because this is where composites are much different from let us say metals for design applications. So the good thing about composites is you are designing the composite material itself. Unlike in metals, where you say, okay, now I am picking up aluminum to design a shaft, for example, or let us say you are picking up titanium or magnesium or steel for some application. But with composites, you will see when you want to say that let's say we are picking up, let us say glass epoxy composite, which means glass is the fiber and epoxy is the matrix you have chosen, which means you have a choice for the fiber material and the matrix material. But in addition to that, what other choices can we make? We can say how much is the fiber fraction and how much is the matrix fraction, because the more you increase the fiber fraction, the more stronger is the material. But if you increase the matrix proportions, again the properties can decrease, but the cost also can decrease. So you need to come up with an optimum fiber fraction for a particular application. So which means the volume fraction of the fibers and the matrix is something in the designer's hand. And what else can we change? We can also look into what is the fabrication method to prepare these composites. We can also choose what is the orientation. Do you want these in 0 directions or 90 degrees or inclined? And we can also decide about the number of layers, whether we are going with 10 layers, 20, 30 or 40, and what is the sequence of these 10 layers we have chosen, because we said all of these will influence the effective properties of these composites, which means all of this is just part of material design, I would say. We are not even going into structural design, because structural design starts when we have a laminate. When we have a laminate, then you are looking at how do I use that laminate to design, let us say the wing of an aeroplane or the fuselage of an aeroplane or a bumper of a car. So that is a structural analysis. But even before we go there, at the material level itself, we have this design options to be chosen. Because of these options, it has few other advantages, such as now we can save material, meaning there is less wastage of materials. Unlike metals, where machining and all is a reduction process, where you remove the material to come to the final shape or size, whereas in composites you target to the final dimensions, which means the amount of material wastage is very less. And another very major advantage, I would say, is when we were designing, let us say for example this pen, right, let us say the application I am designing this pen or this member is for an axial load, which means we want to have this structure or a member with very good properties along the direction. But what about the perpendicular direction? It could be some moderate values. You really do not need these very high values in the perpendicular directions. But what happens in metals? Because metals are mostly isotropic materials, meaning that you will have the same properties both in all directions, both along the length of the member as well as perpendicular to the member. So, but if I go with, let us say, the fiber reinforced composites for this particular application, now that I know the loading is in along the length of the member, once I have the fibers along the length, these properties are good along the length. But in the perpendicular direction, since I already know there is no expected loading in that direction, I need not give superior properties in that direction, which means I am able to save some material, or I am not over designing in other directions. So, essentially to say that we are avoiding this over designing in the other directions where we already know that there is no load or not much stresses to be concerned about. Okay. This is all into these the advantages we are getting because of tailoring in the design of composite material. So, now going to the fatigue life, there are many applications where the loads are cyclic and fatigue life of a structure is of a primary concern. So, again with aerospace and automotive components, most likely the failures, in fact in industry or the reality, 90% of the failures are mostly related to fatigue failure. But with when we compare composites with metals, we see the fatigue resistance or the fatigue failure resistance of these composites is higher compared to metals. And this is a major reason why composites are used in auto or aerospace structures. But now the question we have is, why do you think composites have a better fatigue resistance compared to metals? The reason is, let us say these are all the fibers we have, and let us say there is a crack which is going. So, let us say the crack is approaching here. So, the crack needs to first fail a single fiber, then it needs to fail the second fiber, meaning it has to, the crack is obstructed by each and every fiber. So, the more the fibers we have, the more is the obstruction to the crack growth or the fatigue crack growth. So, naturally in the composites we have lots of these fibrous materials, and these fibrous materials naturally hinder the growth of the crack. So, the fibers naturally hinder fatigue crack growth. In fact, this is one of the findings during the World War. People found that there were cracks happening in the ships and aeroplanes made up of continuous sheets of metals. Once they noticed that there is a crack, the crack grows unhindered, meaning there is no nothing to stop the cracks. Then in those days what people have done is, instead of using one continuous sheet to make either a ship hull or these aeroplane wings or the fuselage, they have joined pieces of sheets of metals using riveted joints. The idea here is, let us say if there is a failure in one of the sheet, but this crack should go from one part to the other part, but to go from one part to the other part, it should go through these riveted joints, and these riveted joints acted as a hindrance for the propagation of cracks. So, that is the one of the reason why they have moved into these riveted joints, and very rarely they had this continuous one single metal sheet or a metal structure, but these are mostly joined. The reason is it hinders the crack. But when we come to the composites, it naturally comes into the picture because we do have these fibers which hinder the crack growth. And another advantage with these composites is dimension stability. There are several applications where we either want the near zero CTE, meaning coefficient of thermal expansion. We do not want the product to change in the shape or the size even though there are changes in the temperatures. And there are some applications where you have to match the CTE with the adjoining. Let us say you are designing a component, but this component is sitting adjacent to another component which is, let us say, bonded or joined. So, how do we make sure that because of the temperature changes there are no thermal stresses build up between these two components? So, the advantage of composites is you can also design such that you can reach a target CTE. This target could be a near zero value, or you can targeting it, let us say now we have a composite which is being joined to, let us say, aluminum. Now that we know the CTE of aluminum, we can design these composites such a way that the effective CTE of these composites is close to aluminum, such that there is no thermal stresses build up at these joints. So, some of the applications are space antennas. Space antennas is a critical application where we do not want any change in the shape, because let us say we are aiming this antenna at one point. If there is a change in the shape, probably it is not pointing towards a target, it is, and this is something to be avoided. So, there is one application, space application composites are used such that the near zero CTE is achieved. Other applications are again space structures. As we know, like there are many, there is a large fluctuation in the temperatures of space structures. Let us say we are talking about a satellite orbiting around the earth. When it faces the sun, the temperatures are high, but when it is in the other end of the earth, the temperatures are low, which means in each cycle it has to see a big variation in the changes of temperature. So, then CTE again is a concern if it is not properly addressed. So, now that we can use composites to target to a desired CTE, so most space structures use composites to overcome this thermal fatigue. Okay. Corrosion is one more criteria when designing structures, especially when composites are made with polymer or ceramic matrix. They have a good corrosion resistance against the chemicals or the environments in which they are used. What it means is the maintenance required for these composite structures are minimal or sometimes almost negligible. So, one of the example is the glass fiber composites which are used underground in underground storage tanks, because you know in the underground storage tanks there is humidity involved, and since these glass fiber composites are more resistant to humidity, or which means the corrosion is not there, unlike in steel pipes for example. So, they have a better advantage over these metallic structures. So, though as a material the composite might be expensive, but if you are looking at the overall costs involved, there are many cases where the composite structures are less cost effective, or which means they are cheaper compared to the metallic structures. The reasons are because there is less material wastage, which we have already covered, and the other important point to be made is less number of parts. So, let us say the same structure is one made with composite and the other designed with metals. Usually the metallic structure will have more components because it will have lots of, let us say, rivets for example, but in composites those can be bonded. But not just this, there are other ways. The manufacturing methods also ensure that usually composites are prepared in one single component instead of joining and others, which means there are less components. When there are less components involved, of course the overall costs also come down. And we are also seen just in the same slide that there is less maintenance, one of the reason being they are good with corrosion resistance. So, what it means is when we are talking about the cost involved along the life of the component, not just the material, but the cost to fabricate this structure as well as to maintain this structure. If all these costs are involved, then composites definitely have a better advantage over metallic structures. Lastly, they also have good advantages with conductivity. It could be, there are applications where you really need conductivity, and there are other applications where you really want an insulator, which means a poor conductor. One of those examples, one of the points here is electrical non-conducting. Let us say if you are using glass, glass is a non-conductor of electricity or a poor conductor. So, applications where you want to use composites where poor electrical conductivity is required, glass polyester is one good example where it is used. Some of these ladders earlier were made with metals like aluminum, which is light, but recently they have been using these glass polyester ladders because they are less electrical conductive, especially people who are using ladders for electrical maintenance and all. This is definitely a much safer option compared to the metal ladders. And there are other applications where we really need conductivity. For example, if we use copper matrix, this is a metal matrix. There are applications where people use copper matrix just to increase the conductivity of these composites. In addition to that, there is a lot of research happening these days where people are trying to develop conductive polymers, meaning in general we know polymers are less conductive, but if we add some conducting material into it, let us say carbon nanotubes or carbon nanofibers, or even let us say metallic spheres, micron size or the nano sized spheres, then we gradually increase the conductivity of the polymers. So, if we use this conductive polymer as a matrix material and with a fiber, even if it is glass, we can improve the conductivity of these composites. And there are some applications where conductivity in composites is good, such as in EMI shielding, which is used to shield the electronics, as well as sometimes it can also be helpful in the health monitoring of composites. But these are advanced research topics which people are working on currently. So, we will now move on to the applications of composites. Until now we have been looking at the advantages. We have seen there are several advantages the composites can give with compared to the metallic structures, but let us see the different applications. Of course, there are several applications where composites are used, but we are only here trying to focus on few of the important ones. So, the major application is definitely the aerospace industry, where it is used to build aircrafts, launch vehicle as shown here. As an example, the Mangalyaan satellite is shown here, but there are also applications such as the space telescopes, which are used to look at galaxies and all. They are also made up of composites. Additionally, even these helicopters where we need lightweight are mostly made up of composites. The reason why we are using composites in all of these applications is primarily because of their good specific strength and stiffness. But in addition to that, we have already seen we have these advantages where we can tailor the design of the composite material itself, as well as the good fatigue resistance, which is primarily of importance in aerospace structures. So, some of the examples of composites are like these carbon epoxy composites or the carbon-carbon composites. Carbon epoxy composites are used where you need high specific strength and stiffness, but carbon-carbon composites we have looked in the previous video where we said these are used where the operating temperatures are high. For example, if we are looking at this launch vehicle here, we see that it is made up of different stages. So, this is the first stage, which is the solid propellant, and second stage is either the solid or the liquid propellant, and last stages, the third and the fourth stage, these are either made up of the liquid propellant or cryogenic propellant. In most of these we see that there is combustion involved, meaning the temperatures are going high. So, for example, in the first stage most of these rocket casings are made up of these carbon-carbon composites because of the combustion of the propellant the temperatures are very high and it needs to maintain the integrity of the structure while combustion. But let me now say that I will try to relate these launch vehicle and the space satellite and see why we use composites in let us say space satellite. So, usually people say that composites are very expensive, we only use whenever there is a real reason to go with an additional cost for an application. So, let us try to see what is the, or guess what is the mass of this launch vehicle or the satellite. So, usually it is in several tons. So, for example, this Mangalyaan mission, the launch vehicle used had 290 tons. Each ton is 1000 kgs. So, now you can see what is the huge mass of this launch vehicle. Okay. So, if you have looked carefully, this is where the satellite is sitting in the launch vehicle, and the mass of that satellite is just 1.3 ton. So, even if in a ratio it is almost like 1 is to 200. So, let us say the satellite mass is 1, then the launch vehicle is 200 times more or more than 200 times. But even if we look at this satellite, it is not like all satellite is made up of structures. So, it also carries a propellant, and then the rest is all called as dry mass. So, in fact, out of this 1.3 ton, only half ton is dry mass, which includes the satellite structure as well as the payload. The rest all is going into the propellant, because it needs the propellant to make the maneuvers while changing orbits and to maintain a single orbit. So, the point I am trying to make is, now let us say we are into the design of these satellite structures. So, whatever small saving in the mass you can make with the satellite structure will have a big ramification when it goes to the launch vehicle, because let us say even if you are saving like 50 grams or 100 grams at a satellite level, that translates into few kgs when it comes into the launch vehicle. I am just trying to give you an example such that you appreciate why composite structures are sometimes used in aerospace, let us say the satellites or even the space telescope or helicopters. So, whenever we save mass, the saving of the mass can go into the saving of the fuel, let us say in the automotives or the aircrafts, and it can also go into lengthening the life of the structure. Okay. Now, let us move into another application, which is the automotive industry. So, we use composites to design the drive shafts in these automotives. We also have composite springs. So, for example, if you might have seen the leaf springs used in trucks, right? Those are sometimes replaced with these composite leaf springs. And these bumpers in the front of the automotive, which can take some impact loads, are also being replaced with composite bumpers, because it saves weight. And the tires used in the automotives, at the face of it, it looks like a simple polymer or simple rubber, but actually this rubber is reinforced with metallic reinforcements, so as it can take higher loads. Similarly, for the brake shoes and the engine parts, in several of these components, composites are being increasingly used. The reason why we are using composites in all these applications is mostly because of low weight. So, when we go to using starting to using composites, we reduce the weight, and the other bigger benefit is it improves the durability of the components. Especially when we are looking at automotives, we are planning to use it for either a decade or longer, which means we need to ensure it is durable, which means it can survive for long times with less loss in the performance. So, then the corrosion resistance benefits the composite brings is of importance, as well as the improved fatigue life of the composites, as well as the impact properties. Let us say we are designing this automotive, we want to make it crash resistant. Composites, especially if you are designed properly, they have good impact resistance compared to the metallic structures. So, similarly, we have applications in infrastructure such as in bridges and buildings, composites are being used. So, sometimes actually composites are used to retrofit or to repair pillars. Let us say we have a pillar which there is a people have found a crack in it. So, usually people use a composite as a reinforcement, so that to maintain the integrity of these columns or beams. One of the reason of using composite as a reinforcement in infrastructure is because of their good corrosion resistance. Composites are also used in the defense applications where protection is required. So, such as in the bulletproof helmets and the bulletproof vests, as well as for the portable bridges where let us say a bridge needs to be immediately be installed. So, it better be made up of composites because it will be made up of less weight and which can be folded and transported in a armed vehicle. So, the figure here shows a bulletproof vest, and in fact it is prepared in IIT Delhi by Professor Naresh Bhatnagar, who works on these bulletproof vests. So, here we have seen a vest. Usually these vests are made up of aramide or Kevlar fibers because they can absorb more energy before failure. Coming to energy applications, wind turbines is one major application where composites are used. So, as you can see here, these turbine blades are huge, meaning like if they are made up of normal materials, because of the mass of this turbine itself, there will be more energy losses. Now, if we use composites, then we can reduce the weight of these turbine blades. So, in fact, since these turbine blades are large, they use a lot of composites, and most of them are made up of glass fiber composites. But there are again different parts of these wind turbine blade where people also use carbon, because especially closer to the rotor where there are higher stresses. Because of the higher stresses you need a high performance composite, that is when they use the CFRP or the carbon fiber reinforced plastic. But we also need aramide, because usually what happens is when they are rotating there are bird strikes, which means birds which are flying, they get hit by these wind turbine blade and it creates a damage into the blade. So, when we use especially the trailing edge where there is a greater chance of hitting the bird, if those parts are made up of these aramide or Kevlar fibers, then they are impact resistant. So, which means there is less damage onto these blades. And of course, we have seen this already, saying that now we can use composites not just for engineering applications, but also for athletic and recreation components, starting with the tennis rackets shown here, but also the golf clubs or the fishing rods, they are also made up of these composites. In addition, these boat hulls are made up of composites, again to reduce the weight, and they are more resistant against humid environments. And the reason why we are using composites in athletics and recreation is essentially it improves the performance by reducing the weight. So, of course, any of us can guess, like old days the tennis rackets used to be much heavier, but now that we are using composites they are much lighter, meaning even kids can actually play more comfortably. This actually improves the performance of the player, and this improved performance is coming because we are able to reduce weight, and that reduced weight is also possible because we are able to tailor the properties based on the necessity, meaning we are only giving superior properties in the directions where it is required, and we are not over designing or avoiding the over designing in the other directions where superior properties are not required. So, finally, let us summarize what we have discussed in this video. We have looked into the advantages and applications of these composites. So, most oftenly cited advantage is definitely the high specific strength and stiffness, but we have seen in addition to that there are several other advantages why composites can be a good candidate, mostly because they can be tailored to reach a specific properties. The dimensional stability also can be tailored either to reach a near zero CTE or to a target CTE. They have good fatigue, life, corrosion resistance and conductivity, which for many applications are very critical. And we have also shown that though the composite material itself might be expensive, but if you are looking at the overall cost, which includes the fabrication as well as the maintenance cost, then there are applications where the overall cost of a composite structure is cheaper compared to the metallic structure. Later we also looked into various applications, though again we mentioned that these are not all the applications we can mention because the use of composites has been increasing with each year. But to mention the more common application, these are aerospace, automotive and infrastructure, as well as the defense and the athletic or recreation activities. So, now that we have seen the advantages and applications of composites, in the next video we will look at what are the different aspects one need to know about the composites, such that you can be a designer using the composites or you can be a manufacturer or an analyst where you are working with composites. See you then. Thank you.